Right, we're looking at 7.3.50. According to data released in 2016, 69% of students in the United States enroll in college directly after high school graduation. Suppose a sample of 223 recent high school graduates is randomly selected. After verifying conditions for central limit theorem are met, find the probability that at most 66% enrolled in college directly after high school graduation. So first, this is our first question. Verify conditions for the central limit theorem are met. So the random and independent condition, it's a drop down. Okay. And then we also have the large samples condition, whether it holds or not in the big populations. And I realize these are drop downs, but we do want to kind of talk through why they hold and what they mean. All right, so I added some language here just to help us as we move through this. The random and independent condition, you need to assume that it or be able to show that it was a simple random sample. And then they must be independently assigned and there must be independence. So what we're going to do for this one, and they do tell you it's randomly selected. So that was given to us in the conditions of our problem. Let me move this down, it's easier to see. So that was randomly selected. So holds assuming the independence is also there. So that's the condition that we weren't told. So for the first one, you would need to assume that that independence is there. Okay. For the second one, the large samples, you have to have at least 10 successes. So what's a success? A success is, in this case, would be a student enrolling directly in college after high school graduation. So our p-value, when you multiply n times p, that's going to tell you the number of successes. And then for failures, it's n times 1 minus p, right? Because the failures would be the complement value or students that did not enroll in college directly after high school. Yes. So at least 10 successes. So if we multiply our n that we were given, right? Well, first, what was our p? We didn't even really talk about that yet. So our p was the 0.69. That was the percent of students in the United States, because that's our proportion, right? That was given for our population. That's the p, the proportion of the population. That's our parameter value. Coming down, we have n from our sample. It was 223. So we need to multiply these. We also need to know our 1 minus p-value, which would be 0.31. So you're taking 100 minus 69, it should be 31%. Because these two numbers need always to add up to 100%, and that's that independence as well. So at least 10 successes. If we do 0.69 times 223, how many successes would we get? 0.69 multiplied by 223 would give me 153.87. Now they do tell you to round when you look in the homework. So 154, because people aren't like parts like that. So in this context, it doesn't make sense. Now for my n times p, it's going to be, and I did that backwards above, it's 223 times 0.31. I don't know. I tend to put the decimal number first. I don't know. That's just something I do in my head. It's multiplication, which is commutative, means order does not matter. Multiplying left to right or right to left, you get the same value. Just like if you commute from your house to work, or you commute from your work to your house, you get the same mileage. That's how I like to think of it at least. And then that would be 69. And if you add those up, they actually give you your 223. So feeling pretty good about what I did there. Both of these numbers are greater than 10. So that means our large sample collection, indeed, it will hold. So that would be our answer for the second. Fill drop down on that question. For the last one, the big populations condition. So our population needs to be at least 10 times the size of the sample. Okay. We picked, our sample was 223. I am going to say, and I can reasonably say that there are more than 2,230 high school like graduates in the United States, right? I mean, there's more than that probably in some, I mean, in some high schools there are for sure, probably. There's definitely more than that number enrolling in college at TCC or FSUT or any institution. So we definitely can say this is reasonable to assume that that can be held, right? So I paused this for a moment because I was a little confused. I was like, wait, what is this looking like? So I mean, what we put is right. It can be held, but can is the word I need to highlight. I apologize. I was like, wait, reasonably be assumed to hold was not part of the drop down. That was our that's the second part of the sentence. So that I don't confuse you, because I confused myself for a second. We can assume that it reasonably holds. So just so the correct word was highlighted, I did go back and check real quick because I was like, that doesn't look right for some reason. It can reasonably be assumed to hold. So it is indeed something that would hold. Good. Now moving on to part B. So part B is going to be the same calculation that we did for 7.3.48. So I'm not going to spend a ton of time going through each step. I would recommend watching that video. But what we will do is we have some information here that we need. That's the beginning parts. Actually, I may actually just move this up a little bit. I know it's the part B, but it's okay. We want to find the probability. This is the part. It's not really part B. They don't call that, but I'm going to call it part B because it feels like a second piece of the problem. At most. So this is really key. So we're being asked to assume the probability that at most 66% enrolled. And that's like that's our success in college directly after high school. So at most is always going to equal less than, well, let's not do equal. It's always going to be, you want to, for that, you want to select 0.66. You want to say it's less than or equal to. So at most always indicates less than or equal to. You cannot be any greater than that value. So we would translate that as our p hat value is going to be less than or equal to the given number. And that's going to be really important because what we're going to be doing, let me go ahead and put my handy dandy little chart back up here. 1 second. Uh-oh, where's my photo tab? What we're going to do here is we are going to be using this normal curve. Okay, we'll leave it like that. But we're going to be using the normal curve. And the idea being if this value, just like we did on the last one, so I will draw this one more time just because I think it helps to see it. We know that our p value is going to be right here in the center, the original probability that we were given. So let me turn this off for a second, and I'm going to come here, come down here. The p is going to be the proportion value, the 0.69. That's the population parameter will be right there. The value that we're being asked to look at is going to be 0.66. So it's going to be over here to the left of that somewhere. We don't know where until we find our standard error. But it's going to be to the left. It's going to be less than. And that's my 0.66. I'll move the other one over in just a second. So that's my 0.66. Stop sharing this. And then if I come back over here to let me move my P over. So P is really the blue. And then I have this 0.66 over here. And we'll make this a picture for later. I'll put it back there because it's not going to like me doing that. I've gone ahead and inserted that, ignore this part, but the value that we are looking for is anything to the left of and up to and including 0.66. So we will be using our normal CDF function again. It's on our TI calculator. Using that normal CDF function, we're going to be putting in our upper bound, our lower bound, Let me go to it and make sure I do these in order for you. I use the calculator to help me. That's what I was thinking. I had that backwards. Lower, upper. Your mu, you will use the P, the proportion for the parameter. And then for your sigma, we do need to calculate our standard error. So that's the only thing we don't have at this moment. So I'm going to pull that formula over. Actually, let's just do it right here. Standard error is equal to, you're going to take a square root of, you're going to multiply your P by the value for 1 minus P. So we've done this enough at this point. It's 0.69 times, here, I'm going to actually insert the formula so you can see it. Is P times 1 minus P over that square root of N. Well, we've already, it's all under the square root with and divided by N. So real quick, we calculated P above 0.69. We calculated 1 minus P. I'll just copy all these down because I think it will help us with our standard error calculation. So just bringing all these things down one more time. We're going to put our square root function in the calculator. Again, I like to actually use 0.69 times 0.31, dividing that by my N of 223. So doing that on the calculator to find my standard error, I'm going to say second square root 0.69 multiplied by 0.31. They should always add up to 100. If you're not sure about your calculation, just double check. If I add those two, is it 1.00, 100%? Dividing that by my 223, I get 0.03097. So that equals 0.03097. And again, we rounded this. We played with this a little in class the other day. It was taking, I would probably do, this one's an interesting one. I'd probably do 10. So anytime you are rounding, if you're under 3 decimal places, if you have a 9 like this is a good time to talk about that because this is an interesting rounding problem, right? If this number is 5, 6, 7, or 8, or 9, you would round up. Well, when you round up here, it's like any other addition problem. If you think about lining up your values, 0.0309, you're gonna do 0, 0, 0, and you're adding a 1 here, right? Well, what's gonna happen when you add the 1 to this decimal place? There's nothing there, so you're gonna have to put in a 0 for that, and the 1 carries over to this position. Do you see that it's going to just carry over? If you're doing normal addition, you're going to bring down your 3. I'm backing these things in. It does not love me doing this. And then I'm going to put, that bring down the 0. So you're really just aligning them in that fashion. So when you add down, this becomes 0. You carry your 1. So you're just rounding up. So 309 rounds up to 310. So sometimes it's easier to think of it in those contexts, but it's a good rounding problem to actually mention that on because we don't often see that. I have not seen it very much this semester, but it does happen occasionally. My p-value was the 0.69. And then for our lower and upper, our lower value for this problem would be negative infinity, right? Because we would start at negative infinity. And then we start this with a purple from negative infinity up to 0.66. That's everything that's shaded. So that's our region of interest. That's the region we're looking for. So from negative infinity up to that point, that's really going to be our 1E99 on the calculator. So let's go ahead and do it together. We do second distribution. We're going to, oops, did not take the distribution. That's my vars menu. So see how that says vars? That's not the right menu. Go back to my distribution. So I hit second one more time. You can always clear out if you're not sure. Just, hit delete, clear, get out of there, start over. Go down number 2, normal CDF. This time, the negative infinity had already been placed in there for me. So that's that. Oh, I didn't have my negative there. Thank you, calculator. So you go from negative infinity up to that p hat value, 0.66. We're going to use our mu, which is going to be 0.69. And then we will use our sigma, which we found to be 0.310, rounding to 3 decimal places. Oh, 031. Oof. All right, it's time for some coffee. 0, 3, 1, 0. And then I will hit enter. And I'll hit enter one more time. And we have 0.16658. So that's going to give me that probability that I was looking for. Bring this down. My calculator said 0.1665866. We don't need all that. We only need 3 decimal places. I looked at it before I came. So we have 3 decimal places here. We're going to use this 5 as our telling us what to do. It's going to round up. So that is going to round to 0.167. And so I did carry the 0 there. You don't have to. Sometimes I do, sometimes I don't. But that would be the probability. So it'd be about 16.7%. Now, in this case, they didn't ask you to change it into a percent, but you could. The probability would be about 16.7%. All right. Again, that is problem 7.3.50.